Yesterday, we learned to add not in the grade 1 way of 3 plus 4 is equal to 7, not in the grade 6 way of 3 plus 4 was equal to -7 or 1 or -1, but rather in a way in which we could add vectors that are not on the same plane. Okay, if we had a 3 and a 4, one of them was to the north, one of them was to the east, how do we deal with that? One of them was to the south, one was to the west, how do we deal with that? Well, remember, the goal is always to get a triangle, a vector diagram triangle. The right angle triangle is easy. Okay, we know what that looks like. The vector diagram, not so much. Vector diagrams are new to us. A vector is a quantity that has magnitude and direction. The magnitude is represented by the line segment. The direction is represented by the arrow on the end of the line segment. If we're adding vectors, then we have to draw vectors. But we have to draw them in such a way that the head of one vector is against the tail of the next vector, or the front of one vector is against the back of the next vector. So if I'm adding these two vectors together, I could draw a diagram like this, or I could draw a diagram like this. Both of those have the front of one vector against the back of the next vector, the front against the back. What I can't do is draw my vector diagram like this, because that's front to front. I can't draw it like this, because that's back to back. Draw a triangle, a vector diagram, right angle triangle, such that the vectors are drawn front to back. Now, there is one more thing so that we actually have a triangle here, because this is only two sides. Triangle has three sides. We also need a resultant vector. And a resultant vector, Cody, goes from start to finish. Right, Cody? Goes from start to finish. You can see in both cases here, this resultant vector looks the same. Right? We could find it, and it would work out to be the same value. We've done it in two different ways, though. Okay, we've done x plus y is equal to resultant. We've done y plus x is equal to resultant. What do we do, by the way, once we have this? Yep. Yeah, we could solve for r. How? Yeah, Pythagorean theorem. It's a squared plus b squared is equal to c squared. Or in both cases here, we'd say r is equal to the square root of a squared plus b squared. Good there? What do we do if we're adding three vectors together? Right? In grade 1, 1 plus 2 plus 3 is equal to 6. In grade 6, 1 plus 2 plus 3 could be equal to something different because we're adding vectors in one dimension in grade 6. Now in grade 11, what do we do if we're adding three vectors like this together that are all on different planes? Cody? Yeah, we got to do x and y components. So for example, maybe we have one like this that's 10 meters, one like this that's 15 meters, and then we have another one like this that's 5 meters. We're going to break it up into x and y components. Remember the goal. What's the goal? Right angle triangle, right? Right angle triangle vector diagram. We're not there right now. Okay, we got to do something to get there. So let's do it. The x component of the first one is 10 meters. The y component is 0. The x component of the second one is 0. The y component is -15. The x of the third is -5. The y of the third is 0. Add these up. And now let's redraw it as a right angle triangle vector diagram. We have 5 to the right. We have 15 down. And we redraw that like this. Lo and behold, that resultant vector that I just drew looks remarkably like the resultant vector that I drew over here. But now it's a lot easier to find because I've got a right angle triangle vector diagram. Now all I have to do is the same thing as I did before. R is equal to the square root of 5 squared plus 15 squared. We okay there? Come a long way in the last 2 days, right? Come from adding 3 plus 4 is equal to 7 to all of a sudden 3 plus 4 is equal to 5, or 10 plus 15 plus 5 is equal to whatever that value of r is. What do we do, though, if the vectors that we're adding aren't so convenient? They're not either x or y, but there's some kind of combination of x and y. Well, the goal is still to get a right angle vector diagram, right angle triangle vector diagram. That's always the goal when we're adding vectors together. But the way we get there is a little bit more convoluted. We got to do a little bit more work to get that triangle. What I want to do first is find components of a vector at a funny angle. You guys remember what 5 words I taught you when you see a funny angle yesterday? Well, that's 2 words. I don't like funny angles. We got an angle of 30 degrees right here. This is one vector, okay, one vector. Let's say it's 10 meters at an angle of 30 degrees. We got to get rid of that 30 degrees, 10 meters. We don't want it anymore. We want to replace it with something else that's either x or y or a combination of x and y. So let's do some trigonometry to do that. We know that cosine theta is equal to adjacent over hypotenuse. Adjacent is the x side, hypotenuse is 10. So x would be equal to 8.66 here. Now we say sine theta is equal to the y component, the opposite side over the hypotenuse, or the y component ends up being equal to 5.0 meters. Look, I had 10 meters at 30 degrees. Now what do I have? Well, basically, now I have this. I know how to deal with this, right? I dealt with this over here. I know how to deal with vectors on the x-axis and the y-axis. It's these ones that give me trouble. So turn these ones into x-axis and y-axis and deal with them the way that we did in the last question. All right, I want you to try one now. I'm going to give you a vector here. It's going to be 100 meters, and the angle is going to be 60 degrees. What do you say when we see that angle of 60 degrees? I don't like funny angles, so we got to get rid of that funny angle. We got to turn it into a nice easy x and a nice easy y. Do that now, please, in the next 1 minute, and then we'll take a look at it as a group. Okay, let's have a look here, guys. We see this funny angle, 100 meters, 60 degrees. We don't like funny angles, so what we do is block it off here, draw a little triangle around it. We're not adding vectors here, right? We're just finding the components of a single vector. But this is part of a bigger project, okay, down the road. In just a few minutes, in fact, we're going to have to be able to find the components of this so that we can add a vector like this to something else. 60 degrees inside the triangle, x component, y component. Let's say cosine 60 degrees is equal to x over 100. That's adjacent over hypotenuse. And x ends up being equal to 50. Sine 60 degrees is equal to opposite over hypotenuse. So y ends up being equal to 10 sine 60, which is 86.6. A couple of people are asking me how we actually enter this. Let's pull our calculators in. Let's make sure, first of all, we're in degree mode. Let's click on mode, scroll down. Sure enough, degree mode is highlighted. So let's clear that. Want to find this 50 meters right here? We're going to say 100 times cosine 60, right? The 100 goes up by multiplying. So literally on your calculator, it's 100 times cosine 60. Looks just like that. Get 50. Then it's 100 times sine 60, and that's going to give me 86.6025. Right? Okay. I'd like to give you another couple examples, but we're just looking at the clock here. I'm going to show you how to put this all together right now. And then if you need a little bit more help with what we just did, then I'll help you out individually with it. All right. What if we have something like this? 10 meters, 20 meters, 10 meters. But the 10 meters is at 30 degrees. That's a vector diagram. Although we don't have a hypotenuse or we don't have a resultant vector label. There we go. There's my resultant. Can we find that? No, we can't because we don't have a triangle, let alone a right angle triangle. So we got to make it into a right angle triangle. And to do that, we know we have to do components, the x and y components. But first, we got to deal with that funny angle because we don't like funny angles. Let's get rid of that funny angle. Let's go over here to the side and redraw it. There's my 30-degree angle. There's my 10-meter length. This is the x side. This is the y side. We're going to say cosine theta is equal to adjacent over hypotenuse. And we're going to say sine theta is equal to opposite over hypotenuse. All right, I'm going to square that off just to remind myself that it doesn't really form part of the main question. It's kind of secondary. It's important. We need to do that because I don't like that 30-degree angle, but it's not the main solution. It's kind of just an aside to the main solution. Now, pay really close attention to what I'm going to do. I'm going to go back to my original diagram, and I'm going to erase this 10 meters at 30 degrees. I'm going to erase it because I just got rid of it. All right, remember I told you when you see a funny angle, you say, I don't like funny angles, and then get rid of it? I just got rid of it. So now I'm going to replace it with what I just found. The x component was 8.66, and the y component was 5. See what I've done there? Now it's a question like I did a few minutes ago, right? We've got 4 vectors now that are all right angles to each other, and I can deal with this. This isn't that crazy now. So let's break it up into x and y components. The x component and the y component of the first one, 10 meters for the x, 0 for the y. 0 for the x, negative 20 for the y. 8.66 for the x, 0 for the y, and 0 for the x, and 5 for the y. We add these up, that's 18.66. We add these up, it's negative 15. We can deal with this now, right? We got 18.66, and we got negative 15. This is my resultant vector, and I know how to find this. All I do is say r is equal to the square root of 18 squared plus 15 squared. Does that make sense? So what do you got to do this weekend in the homework questions that are the last few questions on your worksheet? You've got to take those vector diagrams, and when you see a funny angle, you got to get rid of the funny angle, change it into an x and a y like this, and then go back to the way we solved the other problems. All right, that's it.